when we've been talking about power series, we were kind of restricted to geometric series, and we could figure out what a geometric series converged to. And then we were restricted to derivatives and integrals of those geometric series, and that was all we could do. What we're going to do today is we're going to actually build a power series which has the same behavior as any function. And by same behavior, I mean that it has the same first derivative, second derivative, third derivative, fourth derivative, as far out as you feel like going. If it has the exact same first, second, third, fourth, and fifth derivative as the function, then it behaves a lot like that function on its interval of convergence. So that's our plan for today. So we're going to start by doing this with an example. We're not going to give you the formula until you've already tried it a little bit. So our plan for this example is we want to make a fourth degree polynomial that behaves like natural log of 1 plus x. And we're going to center it at x equals 0, so we want it to behave like that function at x equals 0, and we'd like it to behave like that function for 4 derivatives. So the way we do this is, first of all, let's look at our function. So our function is natural log of 1 plus x. So let's go ahead and take 4 derivatives of that function. I'd recommend that you pause and try to do it yourself, but then I'll talk through what I'm doing for my derivatives after you've tried it yourself. So the first derivative, because it's natural log, would be 1 over 1 plus x. The second derivative would be negative 1 plus x to the negative 2 power, because 1 over 1 plus x is 1 plus x to the negative 1 power. And the third derivative would be 2 times 1 plus x to the negative third power. And then the fourth derivative would be negative 6 times 1 plus x to the negative fourth power. Okay, then we're going to evaluate all those derivatives at x equals 0. And so we have natural log of 1, which is 0, and we have 1 over 1, which is 1, and then we have negative 1, then we have 2 times 1, and then we have negative 6 times 1. Okay, so now we know what our function does at each of those 4 derivatives at 0, so we want our polynomial to do the same thing, which means that we want p of 0 to be just like f of 0. So we want p of 0 to be 0, and noticing that if you plug in 0 for x, p of 0 is just a sub 0. So that means a sub 0 is 0. Now we're going to take a derivative of p. So if I take a derivative of a constant, it goes away. So I have a sub 1 plus 2 times a sub 2 times x plus 3 times a sub 3 times x squared plus 4 times a sub 4 times x to the third. So at 0, that polynomial is really just a sub 1. So that means that a sub 1 has to be 1. Okay, we already know 2 of our coefficients. Now we're going to take a second derivative. And the second derivative, the constant term would go away. So I have 2a sub 2 times 1 plus 3 times 2a sub 3 of x times x plus 4 times 3a sub 4 x squared. So the second derivative of our polynomial at 0 would be just the constant term, 2a sub 2, which means that 2a sub 2 is going to equal negative 1. So a sub 2 is going to be negative 1/2. Okay, Now we're going to take a third derivative. The constant goes away, and we just have 3 times 2 times a sub 3. Do you mind if I write, instead of 3 times 2, do you mind if I write 3 factorial? Because it's really 3 times 2 times 1, because x turns into a 1. And then we have 4 times 3 times 2 a sub 4 times x, which means that the third derivative at 0 is just going to be 3 factorial times a sub 3. So that's going to equal 2. So that means that a sub 3 is going to be 2 divided by 3 factorial, or 1/3. All right, and then we'll do a fourth derivative. And our fourth derivative is going to be, 4 factorial times a sub 4. So 4 factorial times a sub 4 has to equal -6, which means that a sub 4 is going to be -6 divided by 4 factorial, which actually works out to be -1/4, and you can do the math to check that. So what we're saying, after all that work, is we're saying that this polynomial, p sub x equals 0 plus x, 1x, plus -1/2 x squared, plus 1/3 x cubed, plus -1/4 x to the 4th, that this polynomial has all the same behavior as this function, as long as we're close to 0 for 4 derivatives. So it has the same concavity, it has the same slope, it has the same rate of change of its concavity. So it's a lot like this function, and we just built ourselves a power series that looks like this function. And we didn't do it based on the geometric series ratio, we did it using derivatives. I'd like you to notice that this is a lot of work. So you will be doing a lot of work for these problems. All right. Oh, so let's make a 7th order Taylor polynomial for sine of x. I'd recommend that you pause and try to do it yourself, and then you can watch me do it. But if you just watch me do it, it looks easier than it is. But I'm also going to back up for a second and notice some patterns as we were solving this one. As we were solving this one, we noticed that we were always going to be dividing by a factorial. We were dividing by the factorial that even matched the number of derivatives that we'd taken. So, and then that also matched the exponent. So we got to do a little shortcut as we were doing that. And rather than taking a bunch of derivatives of p of x, we can realize that we're just going to be dividing by the factorial that matches the degree that we're on. And that also fits with the constant term because 0 factorial is 1. So if you're worried about that pattern holding for the constant term, it does. Okay, so for this one, our function is sine of x, so we're going to look at sine of x. We're centering at 0, which means the first derivative is going to be cosine of x. And the second derivative will be negative sine of x, and the third derivative will be negative cosine of x. And by the time we get to our fourth derivative, we're actually back to where we started. And then even more than that, if I evaluate these at 0, sine of 0 is 0, cosine of 0 is 1. We're back to 0 again. We're at -1. So the even ones all go to 0, and so the fifth derivative would be back to, would be back to +1. The sixth derivative is going to be nothing, and the seventh derivative would be negative again. Okay, so now we're going to use that factorial pattern that we noticed before. Our first term is going to have a coefficient of 0. Our constant would have a coefficient of 0. Our first derivative is 1, and that's also the same as the first degree. The second derivative would be 0, x squared, technically divided by 2 factorial. The third one would be negative 1 over 3 factorial, and then that would be x cubed, and it's negative 1, and we divide by 3 factorial. The fifth, I'm going to skip the fourth one. The fifth one would be positive again, and it'd be 1 divided by 5 factorial, and it's x to the fifth. And then the seventh would be negative again, 1 over 7 factorial x to the seventh. Okay, so looking just a little nicer, we could write this as x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh. So there's kind of a nice pattern. I mean, it's kind of pretty. The Taylor polynomial for sine of x has odd exponents only. It has factorials in it. It's just really pretty. It shouldn't be surprising to you that the polynomial for sine of x is an odd polynomial, because the sine of x function, remember, behaves like an odd function. It's reflected about the origin. I mean, it's rotational symmetry about the origin. Rotated about the origin. Okay. I'm actually going to leave this one as an exercise for you. Construct a sixth order Taylor polynomial for cosine centered at 0. And maybe, knowing the relationship between sine and cosine, you could find a way to do it using this information that we already have. Okay, I'm not going to spoil the surprise. I'll let you do that one. You can ask in class if you're stumped, but try that one. If you have to, you can do it the same by scratch method that I used for finding sine. Okay, this is the definition of a Taylor series. This is what we just did, but it's written more formally. This is one that's centered at 0. And again, you're always going to divide by the factorial that matches the degree. So if you're trying to build one of these things, you just need to figure out what these derivatives are so that you can build the coefficients. Okay. This Taylor series, when it's centered at 0, is also called the Maclaurin series. This is a special name for a Taylor series that's centered at 0. I don't know why that guy gets his own name. And a Taylor series can also be centered anywhere, and you can center it anywhere that's not 0, then it's called a Taylor series. And the only difference if you're centering somewhere else is, of course, you're going to subtract a because you're shifting, but then you're also going to evaluate your derivatives at that point too. You're not going to evaluate your derivatives at 0, you'd evaluate them wherever you're centered, because you want your function to behave like, you want your polynomial to behave like your function at a, because that's where you're centered now. Okay? So as you're doing tonight's homework, you'll be doing a lot of derivatives, because you're going to have to try to make sure that you've created the right coefficients for your Taylor series, for your Taylor polynomials. Okay, good luck. Have fun. That's your plan.